Okay, so right now we are on question 7 of the first practice exam. So we're comparing the lifetimes of 3 batteries. We have measured the lifetimes of 20 random batteries of each type. Okay, fill out the ANOVA table. Recall, this is another one of the changes that we saw in the course. Okay, I don't expect you to fill out an ANOVA table like I would have, uh, but the main thing that we're going to be doing is you're going to have a data set and you're going to have to conduct the overall F test yourself. Okay, so um, one of the things that we should also have at our disposal, right, ANOVA regression code. Okay, we should have our ANOVA regression code. And so what I'm going to do is fake some data here. All right, so, and you can fake the data yourself. Measured lifetimes of 20 random batteries, 3 types of batteries. Okay, all right, let's fake some data. I'm going to type it in my editor here. Okay, I'm going to put data is equal to R norm 60. Okay, and then I'm going to say data is equal to cbind data, comma, uh, repeat C, which stands for concatenate, 1, 2, 3, comma, each is equal to 20. Bracket, bracket, or not bracket, a parenthesis, parenthesis. And that is the correct code. Okay, so what we have here, we've got our lifetimes. Well, okay, let me make this a little different here. R norm 60, comma 5. Okay, we don't want negative lifetimes. Okay, so just change 60, comma 5. Let's look at our data set again. Okay, so here we've got the lifetimes of our 60 batteries, but we have 20 of each type, right? 20 that are type 3, 20 that are type 2, 20 that are type 1. Okay, and so this is how I would display a data set to you for the final. Of course, it's going to be an Excel file, and you would simply have to read it in, right, in a manner that we've done many times before now, using this last line of the Webull analysis code, right, modified a little bit, and that would simply read the data in, and now it would look like this. Okay? Okay, so as I said, we have 3 types of batteries, 20 lifetimes measured for each battery. Okay, skip this. Using, okay, provide an estimate of the variance, the error variance. No, well, sorry, not error variance, that's regression. Okay, a estimate of the common variance. Recall one of the assumptions for the F test, that what this p-value is from, is that the variances of each group is the same. Okay, so recall the error mean square or the residual mean square is an unbiased estimator for that variance. Okay. So we can do something like this. So copy our first line of ANOVA, and we're gonna modify it. Gonna be kind of a, oh, okay, yeah, we're gonna modify it. Where's my box? Oh, maybe I guess I deleted it. I don't know. Okay, So what we're going to have is this is the variable of interest, which we can see, okay, I didn't do a good job with my labels here, right? Well, normally the labels will be set, in which case you can attach the data set and then use the column labels, okay? But in this case, we're just going to have to use this annoying bracket trick. Well, I don't want to do that. Okay, let's change it. Another line that you might have. Well, it's just to practice the example. It's either call names. I think it's call names. Life, comma, battery. Okay, call names equals C parentheses quotation marks life, comma, quotation marks batteries. That'll give me column labels to work with, okay? So of course normally you wouldn't have, this is not something that you have to remember. Let's type in, that's not gonna work. Call names data. Okay, call names parentheses data. Notice I have column labels now. Okay, so this line of code, not something you need to memorize. The data set would normally come to you like this. Okay, it would come to you already like this, but I'm kind of doing it on the fly on these old practice exams, kind of updating them. Okay, so this line puts column labels. Okay, and now what we can do is attach data. Oh, piece of crap. Okay, so doesn't like that either. So, see, normally you shouldn't have this problem when you're just reading the matrix in or the data in yourself. But since I'm kind of having to do it myself, hopefully this is going to work. Data is equal to data.frame data. Okay. Okay, see, now that worked. See, bunches of annoying steps sometimes. Anyway, okay, so now we need data is equal to data.frame parentheses data. Now we can attach the data set. Okay, again, not stuff that you need to memorize. Normally when you read the data in, it should automatically do this. Or it should automatically let you attach the data. And all the column labels and everything should be done for you. Now that we have that, we can use our column labels instead of this annoying trick, but that's something that also works. Lifetime against battery. And let's see if it likes that. Okay, it worked. Maybe. Okay. We need to put as.factor. Okay. Let me look at this old example. We have to put that. Okay. I was just trying to look at some of our old examples. So you do have to put as.factor on the second column. I'm guessing we did that before at some point. Okay, because it doesn't like that these are numbers. It worked, but it's not treating these as three categories. What it's just treating this as is not categories, but a numerical variable of just like numbers kind of like this. And if it just treats these as numbers and not as categories, I noticed that the degrees of freedom here was 1, and it should have been 2. Okay, it should have been p minus 1, and we have p groups, right? So it should have been p minus 3 minus 1, which is 2. Okay, and one thing we can, where's my exam? Notice that there's 2 degrees of freedom here, okay? It's because it's p minus 1. Anyway, okay, so that might be something you have to do, is put as dot factor on the battery, okay? Okay, so when you read the data set in, it should look like this automatically, okay? You shouldn't have to do any of everything else, but it should look like that. And you should have to attach it, right? You should have to do that. But you have to put this as dot factor on the column that contains the labels of the batteries. Otherwise, you will get a improper ANOVA table, okay? This 1 degree of freedom is representing that it's just treating these column label or the battery labels 1, 2, 3 as just a bunch of numbers and not of actual categories. Okay, so you should always see you should always see 1 degree of freedom less in your category labels as the number of categories. So we had 3 types of batteries. We should see 2 degrees of freedom there. Okay, back to the question. Provide an estimate of the common variance. Okay, the residual mean square or the error mean square is an unbiased estimate for that variance. Okay, from the code, you can do this yourself, but it's not really necessary. If you do this in NOVA, we can see mean square residuals. So this right here is our residual mean square or error mean square, and it is the unbiased estimate for the variance. So just do that. That's much easier. Okay. Don't forget this. All right, let's continue. At the, hold on just a second. All right, at the point 1 level of significance, is there evidence that the lifetime of the batteries differs by type? Okay, provide the p-value and interpret your conclusion in terms of the null and alternative hypothesis. Okay, so this is something you still need to fully understand because I will give you multiple options where something about the sentence is wrong. Okay, now the only thing that's different really in this problem, we're still testing the exact same thing. The only thing is, let's look at our table and not this. So what you're going to have is a table like this. Once you have put in this very similar code, okay, again, as dot factor. Okay, this is our p-value right here, okay? So the only thing we have to really replace in this sentence is the 0.84. Okay, this is how we conduct any hypothesis test, but because the p-value of 0.84, our p-value, is still greater than the significance level alpha, which is 0.1, right? We fail to reject the null hypothesis that the means are the same. The mean lifetimes of the batteries are the same. Okay, to be honest, I'm going to include more than that. That's a pretty half-assed conclusion. Okay, so what this also implies is, right, more specifically, going more in depth, that we do not have evidence of a difference in the mean lifetimes, right? We do not have evidence of the alternative hypothesis that the mean lifetimes are different, okay? So no, kind of like the no decision thing. We do not have evidence that the means are different, okay? Because the p-value, which is 0.84 in our example, our p-value, is still greater than the significance level. Okay, based on the validity of the underlying assumptions of the ANOVA procedure, are you confident in your conclusion? Okay, provides supporting evidence. Okay, so we can verify all of the assumptions ourselves. So of course we assume that we have independent samples and independent populations. One thing is we assume that the variances of each group is the same. All the variances are the same. So box plot life tilde battery. Oops. Okay, just modifying that box plot code to put y tilde x, right? Pretty much. And so again, if you're following along, which I recommend, although I know I had to do quite a bit to get here, your graph is not going to be the same, and also your table here will not be the exact same as mine. It will just should be similar. Okay, should be similar because you faked your own data. Okay, so you should get a box plot that looks hopefully similar. And looking at these, I would say the spread of these, right, kind of how far they span on the y-axis is similar for each box. Right, we do have one little outlier down here, right? This one looks a little smaller, but it's got an outlier. But overall, the box sizes look similar, how wide they are on the y-axis. So that's providing some evidence that the variances of each group is the same, okay? So we can already kind of assume random samples, okay? So the box plot just shows us that we have evidence of equal variances. Okay, and I think we only have one more, right? That the populations, or right, each group is normally distributed. And this is this line of code we could type in. We have to, of course, modify it. Sepal width is our variable of interest, which is lifetime. And then we have our category label as battery is equal to 1. Okay, and then, right, I'm just going to delete this last part. Okay. So copy paste that in, or if you're using this, one trick that you can do is just highlight this and put Control R. But either way, copy paste and put it down here. Okay. So, right, this is looking like a fairly straight line. So it looks like the lifetimes for the first battery appear relatively normally distributed. Okay, and we just have to do that for each group. Okay, again, pretty good. A little more wiggle, not bad though. Not as good. It's got a little bit of curvature to it, so definitely not as good. But it's not horrible. Okay, it's not horrible. So, and that assumption is also, if you recall, the ANOVA procedure is very touchy to equal variances. If the equal variances assumption is violated, then the procedure suffers greatly. However, the normality assumption, the procedure is relatively robust to that, to where if it's not horribly non-normal, right? This is kind of a little more curved, right? Not quite straight, but it's not horrible, right? It's not just way, way off of it, okay? So overall, it looks like the normality assumption is relatively satisfied, okay? So we verified all of our assumptions, okay? Of course, that's for the old problem. Okay, based on your decision in C, is there a need to perform pairwise comparisons of the mean using a Tukey procedure? So in this case, no. Right, our p-value was greater than the significance level, so we did not have evidence that the means were different. Okay, we didn't have evidence that they were the same, right, either, but we didn't have evidence that they were different. Thus, there's no reason to try to look at where those differences are because we did not have evidence of differences. Okay, so right, p-value was greater than the significance level. So we failed to reject the null hypothesis that the means are the same, so we don't have evidence that they're different, and thus there's no need to look for the differences using the Tukey procedure. which we've seen at least a couple times before, and that's where we would have need to modify this line, right? Basically just putting y and then species, we probably still need to put as dot factor battery, okay? So hopefully you're watching, and that's an important thing, is just to recall, right, on the IRIS data set, these labels are not numbers, right? They're actual words, okay? That's why we didn't need to put anything special here. We could just put species because it knows that there are labels, right? Because these aren't numbers, so it knows they're labels. But when we when we have a data set where the labels are just numbers, right? Because that makes it's very easy. We have to put this. You have to put this on your label variable, otherwise you will get the wrong table, okay? All right. In linear regression, what are the assumptions on the error term? Okay, we assume that the error terms, the epsilon i's, are independent and identically distributed normal random variables with zero mean and constant, in this case, standard deviation or variance, okay, sigma squared. Okay, the variability is the same for all I, for each observation. Okay, remember there's 4 assumptions, but all 4 assumptions can be kind of combined into this one statement. Okay, we are looking at time against the integrity of a part. So this is of course one where I'm not going to give you a bunch of graphs, I'm going to give you a data set. Okay. So let's see if I can fake a little bit of data here for us. Okay. Let's see if I can fake some data. 7310. 7310. Okay. 73. Y is equal to 73 minus 10. How many data points do I have? Does it say? I'll just put 100. Who knows? Let's see if this works. All right. No, hold on. 2 to 7. Okay, so just 5. Okay, y is equal to 73 minus 10 times r norm, parentheses 100 comma 5. Okay, again, this is not your memorization, right? Not needed at all. Too much variability. Okay, so just all right, close enough. Okay, y is equal to 73 minus 10 times r norm 100, comma 5, comma 0.3, parenthesis. Okay, so this, and you know what, data is equal to y. Okay, data. Okay, you're going to read your data set in. I'm going to give you 100 observations in an Excel file. Ah, crap. sorry, x is equal to r norm. Okay, x is equal to r norm 100 comma this, okay, and then y is equal to this, and then data is equal to so again, you really only have to do this if you're wanting to follow along, which I do recommend, but normally the data is just simply given to you. Make sure we get some like that on Friday. So x comma y, so this is our data set, okay? And the first thing it wanted was a scatter plot. Oof, that's not what I wanted. Okay, okay, that's a little better. Okay, these 3 lines of code right here will get us a data set that looks somewhat like the problem that we're working with in this example. Okay, which is a scatter plot that looks like this. Okay, so the first thing that it wanted was a scatter plot. So basically I'm saying let's look at a scatter plot of this data. Okay, and it looks like this, so we can see that there does appear to be a linear relationship, right, straight line relationship between the response variable and the predictor variable, and right, there's a negative relationship. As x goes up, y goes down. Okay, so let's fit our linear model. Well, actually, I'll call it data 2. So annoying. Where's our... Oh. Data 2 is equal to data.frame data. Okay, normally should automatically, when you read Excel files in, it automatically makes them data frames, not matrix, and there's really no difference at all. It's just the way R treats them, so it's just kind of annoying. Okay. Ugh, what a pain in the ass. Okay, so here's our data 2, and we're just going to use the brackets because this is too annoying. Okay. So regression model, okay, data 2, bracket 1, data 2, bracket comma 2, okay. Normally we could, if we could just attach this data set, which normally you can do, if you can attach the data set, then all you have to do is put y tilde x, okay. Oops, I got my variables mixed up, right? Y tilde x. You have to make sure you're putting y tilde x. Reg.model. Okay, so first question might be what is the estimated regression line? Okay, and so it is right 70.5 minus 9.5 times x. Okay, and that's y hat is equal to that. And so if we want to look at, if we have a scatter plot like that, if we want to put our regression line, we just have to copy paste that line of code. And so we can see, just based on this plot, that our regression model seems to really fit this data nicely. Okay? See the questions. Okay, interpret the regression coefficients. In the context of the problem, of course, I just said y hat is equal to this minus this times x, right? They're, interpret the regression coefficients. Okay, what is our example talking about? Okay, x is years, time in years, and y is the integrity of a part. So I guess at time 0, right, interpreting beta not hat, when x is equal to 0, when time is equal to 0, the integrity of a part is 70 and a half. Okay, so I guess right when the part is made, it has an integrity of 70 and a half. Okay, interpreting the slope, for every 1 unit change in x, right, that means something for every 1 year older the part gets, we expect the integrity to decrease by 9.5. Okay, so very nice, clear interpretations. That's how we interpret the regression coefficients. Based on the output, does it appear that time is useful in predicting integrity? Okay, so a couple different ways that we can do that, and it says confidence interval, but I'll go ahead and look at both. Summary reg.model. Okay, so one thing we can see is that the p-value is very low, indicating that our x, right, this is our x variable, right, the first column was x, is useful in predicting y, okay, right, and unless otherwise stated, we can compare this p-value to alpha of 0.05, and so we can see that the p-value, right, basically 0, is less than alpha, thus we reject the null that beta 1 is equal to 0, that the slope is equal to 0, and thus the slope is non-zero, and there's a relationship between x and y, between this predictor variable and the response. Okay. If we want a confidence interval instead, we just use confint, okay? And I think it said 95, I don't even know what it said. 99%, okay? Change that to 0.99, confint function, copy paste. And so we have the confidence interval is negative to negative, right? Does not include 0, and thus we have evidence that there's a negative relationship between x and y. And now when you're looking at this, the only difference whenever we're changing the level from 95% to 99%, right, you can still use this p-value. The only difference is instead of seeing if it's less than 0.05, in this case we would be checking to make sure it's less than 0.01, right? And it still, of course, is less than 0.01, so we would still have the conclusion that x is related to y. It's useful in predicting y. Okay. Again, you can read if you want to. Do our model assumptions appear satisfied? Okay, it looks, I'm going to go back to that because that's actually probably different than what we're about to see. So when we're checking the assumptions, we just have to put plot reg.model. And remember, we're going to get this, and if we start clicking, we might think that R is frozen. We have to click on the graphs. So you click once, and let's look at here. So the first thing, first glance, we can see that the red line is fairly straight at 0, right, which is nice. Okay, but we can't stop there. We need to look and make sure that the scattering of points appears fairly random. Okay, so it does almost look like the variance goes up a little bit, and then so that's a little bit strange looking because it looks almost like maybe it's the widest here, and maybe, but there's also hardly any points over here. Okay, so that's probably not that bad. Okay, because well, if this point wasn't here, then that would be a lot worse than it is. Okay, so I might mention that it looks like maybe, say for these lower values and almost even these higher values, you know what, I would mention that maybe the constant error variance appears slightly questionable, because it does look like for this middle range of values, potentially the variability in the residuals, right, kind of looking at how far they're spread on the y-axis, is higher than it is here. Okay, so that actually appears to be a somewhat questionable assumption. Now, besides that, the points appear scattered, right? There doesn't appear to be a pattern or anything like that. Okay, so that might be the only assumption that might be questionable, is that the variance is the same across, right, all x values. We would likely, ideally, right, we want points here. Since we have points here, right, we also want points here and here, and right, likewise, well, not as much up here going on, but it definitely appears that you can definitely see it down here, maybe a little bit up here and here too. Okay, we want basically a random scattering of points, and then this just appears a little bit like it's not, like it's getting more variable here because the spread is wider, and less variable here because the spread is narrow. But besides that, the other ones are fine. Looking at the normality, this looks relatively okay, right? It's great here, right? Goes a little bit off here and here, but that's not bad. Okay. So the only assumption out of the four, right, normality was this assumption, and then the first graph is trying to display 1 if the regression model appears appropriate, and that's, you can tell if there's like a big curvature or something, you can immediately tell that it's not. But you're also looking for the expected value of 0, that red line to be straight. Here, I'll even go back to it. That regression line to be straight. Expected value 0, you're looking to make sure there's not some correlation, right, where the points are just have some usually up and down pattern. And then the constant variance is the one where it does look like maybe the variance here is higher than it is for lower or upper bounds. Okay, as I've said, it's common to have the pattern of where it gets bigger and bigger, but usually it doesn't go back down. Usually it would keep getting bigger. So that's a little strange. Okay. But it looks like for this data set that I generated for this problem, it's different. So we'll also look at these. Okay, this is a horrible one, right? The one we saw looks like the constant error variance was a little bit questionable, but besides that, it looks pretty good. This is one where it's just absolutely horrible, right? Like you shouldn't use this model. Okay, the one we had, it's not, I wouldn't say that this is enough to where I would not use this model. Okay, this is enough to where I would say you should not be using this model. Just immediately, model's no good. Okay, and so, but we can see that there's a clear pattern, right? It's a clear quadratic shape, which not only indicates to us that there's a problem, but also indicates to us that maybe a quadratic component is needed in the model, which is nice. Okay, but going on, if we wanted to, we could also see that this normality plot, right, is fine here, but this is kind of beyond. This is really bad here, right? It just keeps going off. So normality is questionable, and the entire function, our model is highly questionable. Okay, so no good. Does it ask us? Okay, it doesn't ask us to refit the model or anything. Of course, I can ask you in the previous exams. And as I say here, the pattern suggests that a quadratic term may be needed. Okay, so if you see something like this. Now on an exam, if you created your plot, and it looked, if your residual plot, right, that's what that first plot is called, looks like this, that's when you could try adding a squared term and refitting the model yourself. Okay, and it's not needed, but of course what I mean by that, Oh, I didn't type it in anywhere else. What I mean by that is wherever we define reg.model, okay, right, we would need to put whatever x is called, we would need to define the square of x and then put plus that. Okay, so unfortunately I'm using these crappy brackets because it won't let me attach it, but if this is my, whatever x is called, you need to define something like x squared, like you put x2, you can put whatever you want, is equal to, x was the first column, like this. Right? So now x2 is the square of x, and you could just take this line here where we have our reg.model. I might put reg.model2 is equal to linear model y, right? Usually you can just put the column label y tilde x, whatever that x column label is, plus x2, right? What we just defined to be the square of x, and just put plus x2, right? Plus x2. And then that would be fitting the model with the square of x, right? It would be like y is equal to beta naught plus beta 1 times x plus beta 2 times, right, x squared. Okay, that's what adding plus x2 would be, but we have to define it previously. As we've seen before, you'd have to define it. All right, this question, okay, we had to cut the content short. This is the last chapter of the notes, which we did not cover. So that is not a question that I will be asking you. Question 10, you can basically ignore. All right.